Guys, so we are starting from again. I'm telling the same sentence itself, but all are continuation, and in between we'll do a little bit problems, and after that, as the theory goes off, that is completely over, we'll do the a set of problems. Okay, so today we'll start with the topic critical angle. Critical angle, right, and total internal reflection. Right. Now, suppose this can be easily decided or taught by using graph. Now, this is, let's say this is dense, sorry, let's say this is ray, because critical angle or total internal reflection always happens when the ray is coming from denser to rarer medium. So, this is rare and this is dense. This is the incident ray. So, this becomes the angle of incidence, and we saw away from the normal bending. Now, similarly, we are going to draw the same surface. This is normal. Let's say we are increasing the incidence angle. So, angle of reflection also increased further. Okay, let's change that one. Right. So, this is angle of reflection and this is angle of incidence. Now, again, I increase the angle of incidence such a way that, right, this is angle of incidence. We saw that this is our normal, right? The refracted angle or refracted ray is just grazing through the surface, right? So I can say what is the angle now? Refracted angle is 90 degree, right? So I can say the angle of incidence, that is I, at which the angle of reflection is 90 degree, and I can say it is just grazing the surface. That angle of incidence is known as critical angle IC, or it can be just written as C, right? So what is critical angle? The angle at which the angle of incidence at which the angle of refraction is 90 degree and it is just grazing the surface or interface is known as critical angle. Now, if after this third figure I am still increasing the angle of incidence, right, that means now it cannot further go, right? So it will bend like this. That is, all the incident rays has just got reflected. That is, around 100% of the incident ray will be reflected back. Hence, this is known as total internal reflection. So when does the total internal reflection happens? When the angle of incidence is greater than critical angle. So let's write the three scenarios. When incident angle is less than critical angle, a refraction happens, right? So it is, since it is moving from denser to rarer, the refracted ray will be moving away from the normal. When angle of incidence is equal to critical angle, at that time the reflected or refracted angle will be 90 degree, or I can say the refracted ray is just grazing the surface. When incident angle is greater than critical angle, there is total internal reflection. Clear? There is no short form like TIR, guys. I am just writing to reduce my time. Clear? Right? This much is clear, right? So I hope where and all the refraction is happening. So here this is refraction, here it is reflection. Clear? Right. Now we are going for mathematical calculation. If your is asking you to calculate, right? So this again is the interface of two medium. This is rare, this is dense, and this is normal, right? This is the angle of incidence. Let's say this is I, right? And at critical angle, right? Let's say this angle of incidence is critical angle. That's why we found the reflected angle just grazed. So what is R? It is 90. Angle of refraction is 90 degree. Now let's say the rarer medium is having N1 and this N2 is the refractive index of denser medium. So we are going to apply Snell's law. When I apply Snell's law, I can write N1 into sin R, right? Corresponding angle section into N2 sin I. Right, and this we are going to apply Snell's law when the critical condition has been achieved, right? That means sine I has now become what? N2 sine C, right? Sine IC or C. In textbook it is IC, you can write C, it's okay. Now N1, what is sine R? When it is critical angle has achieved, R is 90 degrees. So I'll write it as sine 90 degree. Now what is sine 90 degree? 1. So I will write N1 is equal to N2 sine C, or I can write N1 by N2 is equal to sine C. So what is critical angle? What is N1? Refractive index of what? Rarer medium, right, divided by refractive index of denser medium. That is the critical angle, right? Or what is the nature of refractive index of the rarer medium? It is less than or lesser value, and refractive index which a lesser value will be written above, and refractive index which greater value will be. This is just a short trick, right? Clear? Now if the rare medium, that is here, if the rare medium it is air, right, then N1, what is the refractive index of air? It is 1. So N1 will become 1. So N2, let's say, is the N, which is the refractive index of the medium from where the incident ray is coming. So it is 1 by N is equal to sine C. Clear? Right. So that means this, like this one. This is water. There is a source of light which is coming from here, right? It undergoes critical angle has been achieved, then this is air, right? So 1 by refractive index of water is equal to critical sine of critical angle. This is just an example. Clear? Now sorry, the type of questions which is asked in examination, that is, you are having a surface, let's say this is a medium which is denser, there is this section, right, and this is a rarer medium, right, and this is the corresponding normal and this is the corresponding normal, and you are told the incident angle is like this. It is making 58 degree here. Clear? Right, that is a question, right? And you are asked the path, to draw the path of the let's say path of this ray after refraction, etc., how the path will be achieved. Okay, and you are told the critical angle is, let's say, 48 degree, right? Yeah. Now how would you do it? So angle of incident first of all has been given as 58 degree, right? So I can know now that this ray will be undergoing what? Total internal reflection. When incident angle is greater than critical angle, total internal reflection. Now guys, sometimes you will not be given this 58 degree. Now incident angle will not be given straight away. You might be given this is 30 degree, 32 degree. 32 degree is not the incident ray angle. Incident angle is the angle made by the incident ray with the normal. So this is 58 degree. They can ask like that also. Now this 58 degree is greater than what? Critical angle. So it undergoes what is known as total internal reflection. Right. So total internal reflection means angle of incidence and angle of reflection will be same. So this angle will be also 58. Right. Now for this interface, this angle becomes the incident angle. Let's make this as a triangle. So this is 90 degree, right? So this is 48 means this will be what? 32 degree. That's clear. Now I'm spelling something. Okay. Now this 32 degree, right? Let's say you are told the critical angle is 48 degree. So what it happens, the incident angle is less than what? 48 degree. So it will come out, but it is from denser to rarer medium. So it will move away from the normal like this. Clear? Right? Simple. Right. Now similarly, if the critical angle had been 31 degree, if it had, let's say it is 32 degree itself, right? If the critical angle is 32 degree, then what happens? If the critical angle is 32 degree, that means I have to rub this one. I'm changing the question to make you understand. Okay, if the critical incident here, this for this interface, this is the incident angle, right? So it will undergo grazing, that is not total internal reflection, that is just grazing is done. Clear? I just changed the question to make you guys understand. Now similarly, let's say this is a prism, right? This is 45 degrees, say. This is also 45, doesn't seem so, but I mean it. This is 90 degree. So you are given the incident rays like this, so that the angle of incidence is 90 degree. Again, you are asked to trace the path. How would you do it? Simple, any incident ray which is perpendicular or along the normal will be undergoing no change. So it will go straight away. Right. Now let's say the critical angle of this prism is 42 degree. Right. Now here, what is the normal, guys? The normal is drawn like this, right? It should be perpendicular to the surface. Right. Now what will be this angle? How can I know? This is 90, this is 45, so this will be 45 degree. Right. Now let's take another color. This total angle is 90 degree, right? It's a normal. So this angle will be also 45 degree. Yellow color made is more bad. This is 45 degree and this is also 45 degree. Clear? Now again, I hope you understood the 45 degree. Now for this interface, this 45 degree becomes the angle of incidence. That is angle of incidence. Then reflection angle also should be 45. So this will be 45. So that 45 now becomes 90. I meant to be straight, guys, but I don't know why it didn't become straight like this, right? So this is how the emergent ray comes. This is 45 degree. Clear? Right? Now we'll do another question with numerical section. Right. Prism is supposed to be straight. Okay, I'm sorry if it doesn't look like straight. This is 90 degree. This is the incident ray. Right. And you are just told that it just grazed like this. Right. And you are asked what is the refractive index, and this is kept in a liquid. Okay. Right. To rub this one because I have to draw a lot of things inside. Right, you are keeping this prism in a liquid, and prism is having the refractive index of √2, right? Clear? Right. Now how would you find, and you are told the angle of the prism, let's say, is 60 degree. Right? Clear? This is the type of question you have been given. Guys, how would you solve this problem? Now again, I forgot right now I have wrote the angle of the prism is 60 degrees. It's an equilateral prism. Okay. Now you see in the figure that the angle of incidence is 90 degree. That means it passes straight away. That means this is 60, so this will be 90. So what will be this angle? It will be 30 degree. If this is 30, this is normal, right? I have drawn the normal for this prism. So this section will be 60 degree. That means in this interface, the angle of incidence is now 60 degree. Clear? And I can see when the angle of incidence is 60 degree, the ray grazed, right? So that means this angle of 60 degree became the critical angle. That's why it grazed, right? So what is the critical angle written? It is, sorry, I can write C as 60 degree. Now in the Snell's law, I have written or learned N1 by N2 is equal to sin C. We have learned about it, right? Now what is N1? N1 is refractive index of liquid, and what is N2? That is the refractive index of prism, right? Is equal to sin 60 degree. Why I have written liquid? Because where it is going, right? By where the critical angle has been achieved, or I can say refractive index of rarer medium by denser medium. Clear? Right? I have told about that in the same. That is a less value by greater value. Now, Now NL, what is the refractive index of prism? Root 2 into sine 60 degree, that is root 3 by 2. You will get root 3 by root 2 as refractive index of the liquid. Clear? Right. Now we'll go with the next section, which is circle of illumination. What do you mean by circle of illumination? This is a topic which is not in your textbook, guys. It is a neat topic. Okay. So suppose this is okay. Ouch. Let's take another column. Right. Now this is the interface. Right. This is the denser medium and this is rarer medium. Right. Suppose there is a light source here. Right. So the light source, suppose there is a straight line coming from or light which is coming from this source, it will go straight away because the angle of incidence is 90 degree. Whereas here, say, let's say this face, this is the normal of that surface, the angle of incidence is there. So if it is moving from denser to rarer, so it will bend, right? The next ray, similarly, it is incident here. This is the angle of incident. Again, the angle of incident increase, the bending or moving away from the normal increase. Let's say the next scenario here, right? So again, the angle of incidence increase such a way that now the refracted ray has just grazed, right? That means now this angle is critical angle. Yeah. Now similarly, this situation can arise here also, right? That means this one will be the critical angle, right? Right. So that means we can see the light rays come, but all the light rays will be which are here. That is, say from next incident ray, if it reaches here, it will be undergoing total internal reflection. That means I will not be able to see this one. I will be able to see only this much area. Only this much area, which is like a cone, right? So we can see the light ray coming from the medium as a conical shape, right? So let's say that conical shape I'm writing like this. This is the source here, right? And this is the two ends of the light ray. So this is the incident angle, that is critical angle. Let's say this conical shape's radius is r. This conical shape's height is h. If this angle is critical angle is C, then obviously this angle will be also C. This much clear, right? Now, we know this by looking at this triangle. What is tan C? Tan C is equal to R by H, or I can write tan R is equal to tan C into H, right? Clear? Now, let us make a triangle, guys. Because we have learned about sin C, when it is air and a medium, sin C is equal to 1 by n. N is the refractive index of a medium. So I can make a triangle like this, right? So this is C. So 1 by n means this is 1 and this is n. So this section will be root of n squared minus 1. So from this section or this figure, I can write tan C is equal to n squared minus 1. 1 by n squared minus 1. This by this. Clear? Now I'm going to substitute this value here so that r is equal to 1 by root of n squared minus 1 into h, right? Or I can say r, I am going to write it as h into root of n squared minus 1. That is, sometimes the question is straight away last like this. Suppose a point or a fish is below the water. So what will be its visible range, or what will be the circle of area by which it can see? So area required means I required pi r squared, right? That is a circular surface it can see. So this pi r squared requires radius, and that radius is got by this equation. Clear? Right? Now I will write a simple question, guys, then you will understand. Suppose there is a point 5 meter below. This is a glass slab. See, there is a 5 meter below. Let's match 5 meter below. There is a point. Let's say this is a point, right? The refractive index of this glass slab, right? This glass slab, say, is having refractive index as 5 by 3, and you are asked what is the area through which the light emerges. So again, r is equal to 5, that is h divided by root of 5 by 3 whole square minus 1. You will get r's value as around 15 by 4. Now you are asked what is the area through which the light emerges. This is the area. This much is the area through which the light emerges, right? So I will write it as pi r square. So it is pi into 15 by 4 whole square. Clear? Simple, right? Now the next section which we are going to learn about is application. What and all you see the application of total internal reflection, right? Some of the things you have learned about, which is one is diamond. That is first application, which is easy. Actually it is mirage we are going to supposed to say, but simpler one I will say before, that is diamond, right? What do you how the total internal reflection acts in a diamond? It's very simple, guys. See, in the case of diamonds, suppose I'm going to take this as a diamond, right? There will be a lot of cuts, right? And the critical and the angle of a diamond is so small that all the incident ray which will be incident, that is normal light rays which will be falling on this diamond angle incidence, right, will be greater than the critical angle of the diamond. So it will be continuously undergoing total internal reflection. So that means when you just turn the diamond here and there, total internal reflection will be going on, right? So that's why we say diamond looks very, very beautiful. Clear? Now the next thing which you have to learn about application of total internal reflection is our optical fibers. Now they are used for telecommunication industry, I hope you know, right? And this is basically working on total internal reflection, right? And they are usually very small in size and very light, right? And they have higher capacity for carrying informations rather than metallic wires, right? Now how does an optical fiber work, right? It is actually a high composite glass or quartz fibers, right? And each fiber will be having a core. Okay, this is the core, right? And there will be cladding. Cladding means it's cover, right? And the refractive index of the material of the core is higher. This one is having higher refractive index, let's say N2, and this is having N1, right? I will say N2 is greater than N1. That is, the refractive index of the core is greater than the cladding. Now, as there is difference in the refractive index of core, core will be acting as a denser medium and cladding acts as a rarer medium, right? I hope you understood. So this is rare, this is dense. Yeah. Now when a signal in the form of light is directed at one end of the fiber, let's say like this, right, at a suitable angle, whatever it is, it undergoes repeated total internal reflection along the entire length of the fiber, and finally it comes out of the end, right? How? See, it moves from rarer to dense, right? Then it moves like this, right? And angle of incidence is greater than the critical angle of the core. Then it goes reflection similar like this, and it undergoes. This is how the total internal reflection happens, right? Even if the fiber is bent, light can easily travel along its length. Clear? And this is something you have learned in your life lot, guys, right? The next thing about application of what total internal reflection is working of prism, which we will be taking a lot in the next section. See, prism is designed in such a way that any incident ray it can, right? See, I will take an example by itself. This is a prism, right? Let's say this is 45 degree. This is 45 degree, and so then this will be 90 degrees. It's supposed to look at like a right angle triangle. It isn't. It's okay. Now all the rays, let's say you are having an object, let's say like this, right? This is our B and this is A, right? All the lines are reaching like this, right? At this point, let's say the prism's critical angle is less and the incident angle is having higher than the critical angle value, so it undergoes total internal reflection, right? Similarly here, greater incidence angle, again total internal reflection. So see, so actually this end is of what? A. So this end becomes A. So you will say this end becomes A dash, right? Sorry, this is for B, right? This is B dash and this is A dash. So I can say the object's image has reversed by 180 degree. Clear? Simple. So I can bend the light, right, by 90 degree, or I can even bend by 180 degree. Similarly, so there are some more problems or figures in your textbook. Please go through it. Clear? Now there is a case of mirage which I will take in the next section. Well, I will, because it is out of syllabus, so if the time is there, I will take the small topic mirage also. Okay. Now since we are talking about prism here, we'll go for the next bigger topic, that is prism, right? Ouch. Yeah. Now what is a prism? It is a solid or made of glass, or it can be even plastic. It's you can see, but usually we study is made of glass, right? And it has throughout it has a single refractive index because of the material by which it is made, right? And it has two surfaces. If you draw a prism, right, it is like this. I'm very bad at drawing. I'm supposed to draw a line. Okay. Ouch. Does it look like a prism? I could have drawn two triangles, huh? Right, this is the prism. So this two surface, right, in this, suppose this surface incident ray comes out, the emergent ray might be coming from this side. So these are the two surfaces are called refracting surfaces, and they are usually polished, right? This angle, say the angle between these two refracting surfaces, that is known as angle of prism, or A, right? Clear? And this is the base. Which one? This one, below portion. These are the common terms you have to know. And whereas in our physics section we will be just drawing a triangle in place of prism, we will not draw in the entire prism. This is because it's time consuming, guys. Okay, so I hope you, and there are some of the terminologies in the prism you have to know. You know what is incident ray, right? Ray which is falling on one of the refractive surface, and since it is moving from rarer medium to denser medium, there will be a refracted ray also, right? Now similarly the out ray, that is the ray which is coming out of the second refracting surface, is known as emergent ray, right? Now similarly, when the incident ray is considered or compared with the emergent ray, there will be some deviation between them, right? There is a deviation between the emergent and the incident ray is known as angle of deviation. These are all terms you will learn now in this section. Clear? Now let's move on with the proper prism figure. This is the figure of a prism which we are going to study, right? Now this is the incident ray, let's say. Now this becomes the normal, right? So it is moving from rarer to denser, so it moves towards normal like this. It fall over here, again it undergoes what? Moves from a denser medium to rarer medium. So the normal section is like this, so it moves away from the normal like this. Happy? Right. Now we'll take another color to draw something else. Okay. Now let's say I'm extending this incident ray. Similarly, I'm extending the emergent ray, right? And I'm meeting this point as M. Let's say this prism is named ABC, right? Now I can extend these two angles also. So this is R. Usually this section will be inside the prism itself. If you want, we can make this prism larger one, right? Sorry guys, because I want to have the same figure as that of the textbook. What is the blue color? We'll extend it here. Right. So this is C, this is B. Now this triangle also lies inside the prism itself, right? Let's say this point is N, right? Now, okay, we'll mark the angles and other parameters in red. This is R1. Let's say this is R2, right? Clear? Right. This is rarer medium. The prism is denser medium. Clear? Now this angle is known as angle of prism. Clear? Right. Now let's take this point as Q and this point as R. Right? Clear? Now let's take the quadrilateral A, Q, N, R. This quadrilateral. This is A, Q, and R. Okay. Let's take that quadrilateral. So what can I write about that quadrilateral? You know that the opposite side of a quadrilateral is sum is equal to 180 degree. I'm going to take the angle A plus angle Q N R is equal to 180 degree. Right? Now what happens in the case of triangle? Let's say Q N R, this triangle. This triangle, all the sides sum will be equal to 180 degree, right? So angle R1 plus angle R2 plus angle QNR is also equal to 180 degree, right? Now from this equation I am going to write angle QNR is equal to 180 minus R1 plus R2. Can't I write? Now this QNR is a value which is present here. So there I can write angle A plus 180 degree minus R1 plus R2 is equal to 180 degree. So this 180 degree, this 180 degree cancels out. Hence I can say angle A is equal to R1 plus R2. Now what is R1 and R2? I hope you remember. R1 is the refraction which is happening in the first interface of the prism, and R2 is the refraction which happens in the second interface of the prism. Clear? Oh, sorry, R2 is the angle of incidence in the second interface. Sorry, I thought I was making some mistake where I was telling. Okay, now okay, I have to go for the figure again. Right, I would take yellow color. Okay, now let's take the angle Q and R itself. Q M, this one, and R, this triangle. Right, QMR. Right, so in triangle QMR, deviation, right? So how can I find the deviation? I have to, from that triangle I am supposed to find the deviation. So you have to know what is deviation, right? See, this dotted line which we have, let's say this dotted line, that is the extended form of the incident ray, and this is the extended form of what? Emergent ray. So this is the deviation, because this incident ray, if there was no prism, it would have moved in this direction, but it deviated and it emerged in this direction, right? So this angle is known as angle of deviation. Clear? Right, so this angle is supposed to be written as angle of deviation. So from triangle A and B I can write delta. Let's name some angles 1 and 2. Let's say this angle is 1 and this angle is 2. Right, so I can write, it's an exterior angle, right? So so I have to take the other color. Then angle 1 plus angle 2 is equal to delta, sum of opposite sides of a triangle. So I is equal to, not opposite, I think, sorry, exterior angle, right? This becomes exterior angle, right? Look into the diagram, guys. So I also see in the figure, there is a lot of things we can see in the figure. I have not marked the incident ray. This becomes the incident angle. Now this I is equal to this angle, right? Similarly, this emergent angle, right, is equal to this, right? So I can write I is equal to angle 1 plus R1. Similarly, or I can write this one, I will write angle 1 is equal to I minus R1. Similarly, E is equal to angle 2 plus R2, or I can write angle 2 is equal to E minus R2. Now let's substitute these values there. So delta is equal to, that is deviation, or the angle by which the incident ray is deviating from its path, is equal to I minus R1 plus E minus R2, right? Or I can write this as I plus E minus R1 plus R2. This is the deviation 1 equation, right? Sorry. Now from this equation are some of the things on which the angle of deviation depends. First, it depends upon the prism, right? That means it depends upon refractive index of prism. That is, if refractive index increases, that much will be the deviation, right? That much will be the bending of light. Similarly, angle of prism, right? Now, someone is telling you angle of prism, how would you prove it is true or not? Because we have earlier written angle A is equal to, or the angle of prism A is equal to R1 plus R2, right? So in the above equation, I can even write I plus E minus angle A. So there's another expression for what? Deviation. So the second parameter on which the deviation depends is angle of prism. When A increases, right, deviation increases. As the prism becomes large, deviation will be large. Now third, wavelength of the light. Again, when the wavelength increases, the deviation increases. Clear? That is, in VIBGYOR, if you consider VIBGYOR, right, which is having highest wavelength? Violet, right? So it will be having the maximum deviation. Red has the minimum wavelength. It has the minimum deviation. Sorry. Now the fourth section, angle of incidence. Of course, right? As the angle of incidence increases, right, the deviation decreases. But this is a very important thing, guys. The parameter. This is something which was experimentally proved, not theoretically proved. It was found when the angle of incidence was first increased, the angle of deviation was decreasing, right? Further, I increased the angle of incidence. Now the angle of deviation reached is so much that it becomes its minimum value. After this, when the angle of incidence was further increased, it started, that is, angle of deviation started to further increase. See? First decrease, then became minimum value, then it started to decrease. That means when a graph was plotted by taking the values, this is angle of incidence, this is for deviation, the graph was like this. Initially decreasing, reaching the minimum values for some incidence angle, right? This is minimum deviation, right? And it gradually increased. Not a uniform curve, guys, non-uniform curve. Right, that means from this graph it is clear that minimum, that is deviation is minimum for only one particular value of incidence. Clear? So minimum deviation when it occurs, it was experimentally proved that angle of incidence was equal to emergent angle. Similarly, R1 was equal to R2 from the figure. Right? It was experimentally proved that angle of incidence was equal to angle of emergent and R1 was equal to R2 when it was experimentally done. Sorry, when the minimum deviation occurred. Clear? Right. And another thing which was found was the reflected ray, right, was parallel to the base. These and all are the things which was found during the prism which was undergoing minimum deviation. Clear? Right. Now there are some more things we have to talk about, which is, see, we in this condition, that is what and all happens or when the deviation is minimum, make that as a single heading. we know angle A is equal to R1 plus R2, and we just told that during minimum deviation R1 and R2 is same, so I will write it as common term R, hence A will be equal to 2R, or R is equal to A by 2. Clear? Now, what is minimum deviation? Minimum deviation, we have, what is, let's say, the proper deviation equation. Then we will make it as the minimum. Proper deviation is I plus E minus R1 plus R2, right? And then we wrote it as I plus E minus angle A, right? And what is angle, right? Remember, we have taken, and I just told you during minimum deviation, I will be equal to E, that is angle of incidence and angle of emergence is same. So I can write this as 2I minus angle A. So this now is minimum deviation equation, right? Now, even if you are asked for angle of incidence when minimum deviation is given, then I can write angle A, that is angle prism's angle, plus minimum deviation whole divided by 2. Clear? Right. Now, if you are asked how to find the refractive index, right, by using minimum deviation, or how can I find a relationship between minimum deviation and refractive index? How would you do it? Right. Suppose you are having a prism like this, right? It is having refractive index N2, and the outside surface is having N1 refractive index. Then like this, that is what does it mean? Refractive index of N2 when compared to N1, right, is equal to what? Sin I, right? Suppose the incident ray is in this way, right? Sin I divided by sin R, right? You have learned. Now we just wrote that I, incident angle for during minimum deviation, is delta min divided by 2, right? So here I can substitute this one, so that N2 by N1 is equal to sin A plus del min, that is minimum deviation whole divided by 2 whole divided by, and there is a sin R, right? Now remember, we wrote R is equal to A by 2 when minimum deviation is occurring, R1 and R2 is equal, so 2R is equal to A, or R is equal to A by 2. So I will write here sin A by 2, right? So suppose the medium from where the light is coming, this is air, so N1 becomes what? Air, N1 becomes 1. So N2, I just write refractive index of the prism is equal to sin A plus minimum deviation whole divided by 2, then divided by sin A by 2. This is the relationship between minimum deviation occurring in a prism and the refractive index. Clear? Now, there is a small thing more. Suppose the prism is very small. So that means the minimum deviation will be also very small, right? And then sin theta, the theta angles, etc. will be equivalent to theta. That's how you rate. So in the above equation, I will remove sin, right? When theta becomes so small, then sin theta is equivalent to theta itself, right? You have learned. So in the above equation, I will remove the sin section. So n, refractive index n, is equal to A plus minimum deviation whole divided by 2 divided by A by 2. Clear? Now 2 cancels out. I can write refractive index is equal to A plus minimum deviation divided by A. Right? Clear? Right. Still it is not over. Ouch. There are many equations to by heart. After that we will, or in this video we will not do. In the next video, or the Sunday video, we'll do the problems. Okay. Now, sorry, Monday videos. Now, then this A can be brought here. Then NA is equal to A plus del min, minimum deviation. Or I can take common A outside, then it becomes n minus 1 is equal to minimum deviation. So this is the equation for minimum deviation and refractive index relation for a small prism, whereas This equation, this large equation, is equation which relates refractive index and the minimum deviation in the case of